Okay, so we've set up the scene for the Noether isomorphism theorem. We think about it as being represented in this picture. Um, we need to show, though, that f is a well-defined function. Namely, when we look at congruence classes, which is what R mod kernel is, congruence classes, they are represented usually by an element from the ring that you start with. So we have R plus kernel phi. And what we have to do to show that it's well defined is that no matter which element represents our class, it should go to the same spot. Okay? That's the idea. So let's go ahead and prove exactly that. So let me go down a little bit here. Well, we're going to phrase these all as a lemma. So we say f defined above is well defined. So what does that mean? Well, we need to show if we have two ways of representing our coset, then the outputs are the same. So that, it doesn't matter how you represent the coset, you get one and only one output. All right, so let's do this. So since the cosets are the same, what that means is R2 minus R1 is in the kernel. Namely, the cosets are the same, so they're congruent mod the kernel of phi. Again, the kernel of phi is always an ideal. And so their difference is in the kernel. Well, that means that when we plug them into phi, plug that difference into phi, we have to get 0. Well, phi breaks up under subtraction, and we can add phi of R1 to both sides. So phi of R2 is phi of R1. And that's our first lemma. All right, great. We'll do one more lemma in this video, and then we'll deal with the one-to-one and onto properties in the next video. The next one is f is a homomorphism. Right, so f, remember, was the guy that took R1 plus kernel of phi to phi of R1. Okay, so this is really f of R1 plus kernel of phi. And we need to show it's a homomorphism. So let's do exactly that. Proof. Let's start with preserving unity. Maybe I'll put them in, I don't know, maybe like orange. Let's go with preserving 1. F of 1, the 1 in R mod kernel is 1 plus kernel. I'm not going to subscript the 1. I'm just going to call it 1. That is by definition phi of 1. That's the definition of f. And phi is a homomorphism. So phi sends 1 to 1. And the rest of the remaining two properties, I think I have way too many m's here. The remaining two properties will similarly follow. It'll be like, oh, well, phi is a homomorphism, so f is. So let's see, let's do addition next. So let's take some R1 plus kernel phi plus R2 plus kernel phi. And we have to add them first, and then we need to compare them to plugging in R1 plus kernel phi and R2 plus kernel phi, kernel phi, into F. On the left-hand side, we first add the cosets, and on the right-hand side, we first plug them into F. So F is the I plug you into phi function, so we plug the representative into phi. On the left-hand side, we are now in a position where we can say we can do what f does. It's in the right form. So f is the I plug u into phi function. And we need to know, therefore, if this equation is true. Again, we've just written out the definition of f a bunch of times. And that equation is certainly true, because phi is a homomorphism. I'm just going to say is a hom, but you can write it out if you like. All right, let's now do products. So we multiply inside of f, and we compare that to applying f first and then multiplying. And we want to know, again, are these the same with our cautionary orange? All right, R1, R2 plus kernel phi is how you do this product inside of f. And this guy is going to be phi of R1 for this first one, and then phi of R2 for the second. On the left-hand side, this is, again, plug the representative into phi. And so we need to know, is phi of R1, R2 the same as phi of R1, phi of R2? And that's certainly true, because phi is a ring homomorphism. So what do we conclude from this? Then f, which again, just this is a reminder, it's not part of the proof, but just as a reminder, f is a map from R mod kernel to the image, is a ring homomorphism. All right, in the next videos, we're going to tackle one-to-one and onto.